Okay, so we're going to learn about the multiplication rule. This is a situation where you have two or more trials of an event, or an experiment, I should say. And we use tree diagrams and list sample spaces a lot more frequently for questions like this, or at least consider them, just because the number of possible outcomes can tend to get a little out of hand, and then we start looking for different shortcuts that could come into play. That's where a concept related to combinatorics or permutations and combinations come into play specifically. Right, so in the first example here, we're tossing a coin and then rolling a die. We want to construct a tree diagram for the flip of the coin and the roll of a die and find the probability of getting a heads and rolling a 5. All right, so it's pretty simple in terms of coming up with a tree diagram. It's just an organized structural approach, or structured approach. Structural, that's not the right word. So we have the coin, and we have the die. The coin has two possible outcomes, heads or tails. For each outcome of coin, we have 6 outcomes for die. I'm just kind of sneaking them all in here. 1, 2, 3, 4, 5, and 6. All right, so I'm just going to kind of move this over a little bit. All right. So you have some person who's running their experiment, and they're deciding, okay, I have my first choice. My first fork in the road is I flip the coin, I can get either heads or tails. All right, so then after they've met that objective and got an outcome, then their next fork in the road is making a determination of what the outcome would be for the roll of a die. All right, it could be the numbers 1, 2, 3, 4, 5, or 6. So that actually is a tree diagram. We could throw some probabilities in here if we wanted to, but it's not really the purpose behind what I'm trying to demonstrate, at least for this example. All right, so what I can do instead, so this is the tree diagram. We can pull a sample space from this. And we can do that by just following each pathway. If I start with the person that makes the first choice, that first pathway gets us to heads, and then continues on the journey to get to the number 1. Our first outcome would be heads followed by a 1. Then we can start the journey, get to heads, go down the next pathway to get us to a number 2. Looks a little elliptical, but that's okay. So heads 2. And we can keep doing that until we get through all the different possible outcomes for heads. So heads 3, heads 4, heads 5, heads 6, and then we would do the same thing for tails. So start the journey going down in the direction of tails. Ooh. I don't know why I expected that to autocorrect for me. And then our decision could take us in the direction of 1, or 2, or 3, or 4, or 5, or 6. So T1, T2, T3, T4, T5, T6. So looking at that, we can make a determination. You say it's probability of getting a heads and rolling a 5. We could look at that as saying, okay, well, isn't that really the same as this outcome? We get a total of 12 outcomes here. Count them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes. One of which is the one that we want. All right, so obviously the rule we're learning here is called the multiplication rule for a reason. If we have what's called independent events, what we can do is actually just multiply the two probabilities. The independent events in this simple, a very simplistic way, is really just kind of stating that two events have no interaction with one another, in the sense that one event occurring would have no impact on the other event occurring, right? But life is very dependent. For example, if my son's bus comes late, I get to work late. right? It's conditional. They're dependent on one another. But whether or not I get to school on time or get to work on time is not necessarily dependent on whether it rains in Tulsa. All right, so, or at least if it is, it's in a very chaos theory sort of way. All right, so this is along those lines. If I get a heads when I flip a coin, that's not going to impact whether I get a 1, 2, 3, 4, 5, or 6 when I roll a die. So I get a 1 in 2 chance of getting a heads. I get a 1 in 6 chance of rolling a 5 for a product of 1 over 12. All right. Now, if they were all that easy, then we wouldn't have to take a course on that involves probability in statistics. All right. So obviously, the focus would be on dependent events as well, and so that brings us to the next set of problems. So when we look at dependent events, we have to look for certain keywords. These kind of questions kind of lend themselves well to decks of cards because we can replace a card after we draw from a deck, or we can not replace it. All right, so these cards we're going to focus on without replacement, meaning you select a card at random from a deck, and then you don't put it back in the deck before you make a selection for the second card. All right, so if we're looking at something like a king, then an ace, we're saying specifically, I want the probability of getting a king, and then knowing that we got a king, we want to get the probability of getting an ace. So the way we write that is like this, that little vertical line, which means given, or knowing that. All right, so this is read as the probability of getting an ace, knowing that the first card that was selected was a king. So if we know that there's 4 cards in the deck that are kings, I select one at random. It turns out we always assume success in probability. Always assume success. All right, so I assume I got a king. I didn't get all 4 kings because I only selected 1 card, but I'm going to assume I got one of the kings, which means I'm now short 1 card in the deck. So I'm down to 51, but I still have all my aces. So I still have all 4 of those. So I just do a little multiplication across the top, across the bottom, and I get 16 out of 2652. Don't get the wrong idea. I know the 2652 is the product of 52 and 51 because I've been doing this for like 20 plus years, not because I'm a genius. There's a little bit of genius element in this, but not because of that reason. All right, so king and an ace. This is implied to mean either order. All right, so it's saying that the 2 cards that were selected were a king and an ace. So it could mean that we got a king and then an ace. That was weird. Or maybe we got the ace then a king. So we interpret this as, exactly the same we did for the first part, same way we did, I should say. King times the probability of getting an ace given that the first card was a king, or means plus, it's always going to mean plus, it's the addition rule. Or, so this is like a reset, start the whole thing over. New problem, basically. All the cards back in the deck. Another alternative situation would be, and maybe we got the ace first, and then the king. But if we got the king as the second card, we're assuming that we got the ace as the first card. All right, so computations here are going to be exactly the same, 4 out of 52, because there's 4 kings in the deck. Once I remove 1, I'm down to 51 cards overall, but I still have the 4 aces. Start over, shuffle the deck up, there's a 4 in 52 chance of getting an ace. Once I select a card, turns out it was an ace, I'm down 1 card total, but I still have all my kings. So I still have my 16 over 2652, but I have a second 16 over 2652, which gets us to 32 over 2652. And so what we want to do as we go forward is get to a point where we can answer this kind of question without having to write all this stuff out. All right, that's going to be a kind of a big part of the challenge. So next up would be 2 cards of the same suit. And so as long as you know what a suit is, not the kind you wear, but in the deck of cards, and again, you've seen me try to draw them, you got a heart, and a diamond. This is going to be beautiful. A club, and a spade. Right. So what we're going to do is account for the fact that it could be a heart and a heart. So I'm just, for the sake of making things as simple as possible, heart, diamond, club, and spade. Right. So we're looking for the probability of getting a heart and a heart. We're looking for the probability of getting a diamond and a diamond, a club and a club, and a spade and a spade. But we're not getting them all concurrently. We're getting them all in, one in option in lieu of the other. So these are either or situations, or just ors. So this translates to the probability of getting a heart multiplied by the probability of getting a heart given that the first card was a heart. So what I would say here is, okay, well, how many hearts are there in the deck? You can count. Maybe not. You can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Or you can look at the, the structure of the deck and say, okay, well, there's 52 cards, a quarter of them are each suit, a quarter of 52 is 13. Either way. So 13 out of 52 would be the probability of getting a heart. Now, I drew a card from the deck, I withdrew a card from the deck, I pulled one out. Turned out it was a heart. Yes, I got a heart. That means there's one less card in the deck. It also means that there's one less heart in the deck. So, if I can get this to go straight, that tells me that I have a product of 156 out of 2652. 13 out of 52 times 12 out of 51. You get that decimal, but you can convert it over to a fraction. If you want, you can make it 1 over 17. That's fine. I say leave it this way because we haven't finished the problem. We haven't finished the other parts of it. Now, the diamond and diamond would have the same general structure because an or is a reset. So it would have the same breakdown because there's the same number of diamonds in the deck as there are hearts. So computationally, we're actually looking at the same thing. So it kind of begs the question, it's a good question, do I have to do this computation 4 times if I know that my answer is just going to be what I get for the first outcome multiplied by 4? And the answer is no. You just do it the one time, multiply it by 4, and call it a day. All right. I'll show the work though, just so you have it. But knowing that it's really unnecessary to do, you don't want to go too crazy. All right. I got to change my D's to C's here. I'm going to shuffle some things around. You know, my C's to S's, or my D's to S's, either way. So clubs, spades. All right, so you add it all up, because addition rule tells us to add. And we get 624 over 2652. Or we could have just taken this one answer at one computation, just this one guy over here, and said, we're going to have 3 other scenarios that are just like that. Why not just multiply that by 4? 3 other scenarios in addition to the one that we have, and we'll have it. You know, 624 over 2652. All right, so you can get it that way also. A lot of options. Resize. Now it says 2 cards with the same value. Well, that could mean a lot of things, but it also is something that we could, apply what we learned from number 3 to. All right, so 2 cards with the same value would be 2 and a 2, or a 3 and a 3, or a 4 and a 4, 5 and a 5, 6 and a 6, 7 and a 7, 8 and an 8, 9 and a 9, 10 and a 10. Now, jacks, queens, kings, and aces don't have, as in ordinary structure of a deck, don't have numerical values, but there are equivalent in value to each other. Like, all the A's are equal to each other, they just don't have a number. It's not like blackjack where it's 1 or 11. All right, so we would go all the way up to A and A. All right, and so what we learned in the previous question is, since each card is represented in the deck 4 times initially, all I'd have to do is figure out the first computation and multiply it by the number of pairs that we would have. All right, so here we're looking at 13 pairs. All right, and all that is just counting. How many 2s do I have? I keep looking in the wrong place. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right. The 2 occurs 4 times, 3 occurs 4 times, and so on, but each unique card is represented once. Emphasis on the word unique. All right, so 13 pairs is what I'd be looking for. All right, so I would look for the probability of getting a 2, multiplied by the probability of getting a 2, knowing that the first card was a 2. All right, there's 4 cards in a deck that are 2s out of 52 overall. If I select one at random, turns out I got a 2. Yay. I mean, there's only 3 left. And there's only 51 cards left overall. Right? So that's going to give me a result of 12 over 2652. So I can use that and the knowledge that there's going to be 13 pairs to go the rest of the way. So multiply by 13. Gives you a result of 156 over 2652, and that would be your probability. Otherwise, you'd have to do what we did here, instead of 4 times, 13 times.